I could be convinced to accept things on that Monday, but you know how flexible I am with deadlines already. Groovy. So let's carry on talking about series. We have the definition on the board. A series converges if the sequence of partial sums converges. So whenever you want to show any statement about an infinite series, really you want to show some statement about a sequence of partial sums. The two things left in this pattern are like the two examples of series that, without using any fancy tools, you can compute on the nose. And here they are. The geometric series. For any number p, if the absolute value of p is less than 1, then the infinite series from k equals 0 to infinity of p to the k. Oh, so notice this sum is starting with a k equals 0 as the starting index, not a k equals 1. All right, that's just fine. You know what it means for a sum to start at 0 instead of 1. Yeah?
What can you do? Every time I do one, we're getting closer to that.
1, 1, 2.
Okay, yeah.
If p is bigger than or equal to an absolute value, then that infinite series diverges, which hopefully you all remember. That's what geometric series is. Let's try to prove that. And maybe it's worth doing. No, let's just prove it. So I'm going to focus on the convergence results. The other ones really are the same. Let's consider any p and r. The proof of this proposition is built on a lemma. I'm not going to prove the lemma. As a bonus on the homework part today, you will prove the lemma. So it's possible to exceed 100% on this particular homework. Here's the lemma. For any p other than 1, the sum from p equals 0 to n p to the k is equal to that. That seems familiar, I hope. And there are lots of proofs. One of them is by induction. One of them is you could multiply the 1 minus p to the other side and try to prove that equality. So let's now just assume that lemma and try to prove the claim. So I'm going to take the case that p is less than 1 absolute value. I want to show that this infinite series converges. To show an infinite series converges, you need to show the sequence of partial sums converges. So let's start by talking about the sequence of partial sums. And in fact, we have a formula for the sequence of partial sums, don't we? By lemma 5.5.4, this lemma, the sequence of partial sums for the infinite series is given by, let's give it a name, t sub n, is the sum from k equals 0 to n of p to the k. And what is that sum equal to by lemma 5.5.4? Yeah.
1 minus p to the n plus 1 all over 1 plus, 1 minus p?
Yeah. All right, so there's the thing we need to take the limit of. And there are sentences written after that, but if you saw this thing and you wanted to take the limit as n goes to infinity, what would you want to do? And don't think in terms of calculus. Think in terms of calculus, not in terms of analysis. If you saw that in Calc 1, limit as n goes to infinity, what would you do?
Do the fraction rule or whatever, and just see if you go out, what happens to the fraction of the two.
Cool. As n goes to infinity, what does 1 minus p go to?
Pretty much negative p.
No, it's 1 minus p.
Oh, wait, 1 minus p.
There's no n. It's constant. As n goes to infinity, what does the top go to? Careful. P is less than 1 in absolute value.
So 1, yeah.
Yeah, what does, if you take something like 1/5 and you raise it to the nth power and let n get big, does that get small? So, tell me, what is the limit of, so let's now just put that into ones. Since p is less than 1 in absolute value, what's the limit of p to the n plus 1 as n goes to infinity?
1. Is it 1? It's not 1 here.
0, right? If you take something less than 1 in absolute value and start raising it to a really big number.
Oh, less than 1. Oh, what am I thinking? Yeah.
All right, so the only thing that has an n in it goes to 0. So by limit laws, where does t sub n converge?
I'm sorry, can you repeat that?
Yes. So we've now computed the limit of the only piece of t sub n that has an n in it. So by limit laws, where does t sub n converge? We'll read it again. Yeah. 1 over 1 minus p?
Yeah.
Yeah, okay, cool. So,
But P isn't. Oh, P is just some constant. Oh.
yeah, p is just a constant. All right, have we now computed the limit of the sequence of partial sums of the series? So have we computed the limit of the series? Have we computed the series?
Yes.
Yeah. So the sequence of partial sums converges to 1 over 1 minus b. In conclusion, the series converges to 1 over 1 minus b. People feel pretty good? So that's the proof, at least in the case that p is less than 1 in absolute value. So all of the times when it converges. I guess we need to show that whenever p is bigger than 1 in absolute value, the thing diverges. Yeah. So there are 3 other cases to think about. The case that p is bigger than 1 in absolute value, that p is exactly 1, and that p is exactly negative 1. I'm only going to do one of them. But you get to choose which one. So which of those 3 cases would you like to talk through?
Absolute value of P greater than 1.
All right. Let's do it by show of hands. Absolute value of p bigger than 1. All right. 7-ish. P equals 1 on the nose. 1. P equals negative 1. All right. I guess the election strategy of the false vote only counts gave the same result as plurality in this case. So, let's do it. Let's suppose that absolute value of p is bigger than 1. Then I need to do the exact same thing. I need to compute the limit of the sequence of partial sums, and in fact, compute the limit is the wrong one. I need to show the sequence of partial sums diverges. So let's try to do that. Do I have a formula for the sequence of partial sums? Yes. This lemma applies in every case except the case that p is equal to 1 on the nose. But p isn't equal to 1. P is bigger than 1 in absolute value. So we've skipped that case. 1 minus p to the n minus 1, n plus 1, over 1 minus p. Let's explain why that diverges. As n goes to infinity, what does p to the n plus 1 do? Yeah.
Goes to negative infinity. Right? Yeah. No, yeah, you're right. Well, I'm totally wrong, but you're right.
Let's think in terms of examples a little bit. So let's suppose q is like 2.
Okay.
What does 2 to the n plus 1 go to as n goes to infinity? Let's see, this would be the sequence that's when n equals 1 would be 4, then 8, then 16, then 32, then 64. What's that limit?
Infinity.
If you're an infinity. What if you want negative 2? Then what would it do? So then it would be 4, then negative 8, then positive 16, then negative 32, then positive 64. What does that do as n goes to infinity? It diverges. Notice, did it diverge even when it diverged to infinity in the previous case? Yes, let's not try to be fancy and say anything specific. Let's just say this diverges.
What would the algebra be on that? Is it like 1 minus the quantity of p to the n plus 1, or is it 1 minus p, or plus like negative p n plus 1?
Oh, yeah, order of operation says exponentiate lost.
Oh, okay. Yeah, so okay.
Yeah. But if p has a negative sign next to it, that negative sign is also getting exponential. All right, so that thing diverges. So now let's appeal to limit laws. So by limit laws, 1 minus p to the n plus 1 diverges, and 1 minus p to the n plus 1 over 1 minus p also diverges. Thus, Tn diverges. Does that feel pretty okay? I don't know. I guess like we could say something about the case that let's take the p equals 1 case and study that at least a little bit. So in that case, Tn is the sum from k equals 0 to n of 1 to the k. But what's any power of 1 equal to? 1. So this is the sum of a bunch of things. Every term of that sum is equal to 1. And how many terms are there in that sum? Well, it's easy to have an off by 1 error. Yes. If we wanted to take the limit anyway, yeah. So there are k plus 1 terms in that sum. So this is just, n plus 1. So Tn is just n plus 1. What can you tell me about n plus 1 as n goes to infinity? What's the limit as n goes to infinity of n plus 1?
Infinity.
Yes. Yeah, right. Cool. Which diverges, so the sequence of partial sums diverges, so the whole thing diverges. I didn't give you one of them. Okay. I really shot at your table. Did anyone else not get one of these? Is that before they talk? They are also on the webpage. Cool. So, here's one example of a series we can compute on the nose. Here's the other type of series which we can compute on the nose, the so-called telescoping series. Proposition. Let Cn be a sequence which converges to some number C. Let AK be the sequence that's given by the difference between two successive terms in the C sequence. Then, the series that you get by adding up all the AKs converges to C1 minus C. Does that seem reasonable? And like maybe you could do like the intuitive thing, or well, what is that? And the sum of all of the AKs is the sum of all things that look like CK minus CK plus 1. So that's C1 minus C2 plus C2 minus C3. And it kind of keeps on going. And some terms cancel. And I guess if you go from k equals 1 to n, you would keep on going until you did Cn minus Cn plus 1. And all of the inner terms cancel. What's the limit of that as n goes to infinity? Well, as n goes to infinity, what does C1 converge to? Yeah, there are no n's in it. As n goes to infinity, what does Cn plus 1 converge to? Yeah, just big C. Right, the Cn's converge. This is a subsequence of a convergent sequence.
Oh, okay, so it converges to, okay.
Cool. So that thing to the side, in some sense, is all of the content of the proof. But let's actually write the proof. So it's that Cn be a sequence which converges to some number C. Let's let An be given by the difference between consecutive terms. Let's let Sn be the sequence of partial sums for Ak. Then maybe the first reasonable thing to do is let's expand out what that sequence of partial sums is. So by the very definition of Sn as the sequence of partial sums, what does Sn mean?
Sn is equal to the summation notation, like the sum from k to 1 to n of a sub k.
Cool. And now maybe I'll expand that just a little bit further. What is Ak equal to? Yeah.
Ck minus Ck plus 1.
All right. Now there's a lemma that I haven't stated verbally yet, lemma 5.5.6. What does lemma 5.5.6 say about that sum?
That the sum, that partial sum that we just created is equal to C1 minus C sub n plus 1?
Yeah. And if you like, that's exactly what happened in this line. There's the intuitive argument for that. Not a proof. Lemma 5.5.6 is one of these things that I'm saying is proven in homework as a bonus problem. All right. So now let's use elementary limit laws. So the limit of Sn, limit of the sequence of partial sums, is equal to the limit of C1 minus C sub n plus 1. As n goes to infinity, what does that converge to?
I'm sorry, I've written that somewhere. Could you repeat that?
C1 minus C.
Yeah. The question is, what is the limit of C1 minus Cn plus 1 as n goes to infinity? But you already told me that in this space when I talked about this up here. And I should distinguish my lowercase c's from my uppercase c's. There, now you can definitely tell that that's an uppercase C. Nice. Does that mean that I have successfully computed the series? Cool. Nice. People feeling pretty good? So I think I want to vary a little bit from what... Oh, well, wait, no, there's a corollary, yeah. So we have these tools that we can use to show that series converge. Let's use these tools to show that a series converges. Corollary, let AK be that sequence, the sequence AK equals 1 over k times k plus 1. I claim that the series that you get by adding a whole of the AKs converges. Let's try to prove that. And this is it's a corollary, so it should be a corollary of the thing that we just did. So presumably that means that I can rewrite this thing as a telescoping series in a reasonably good way. So let's do that. So in order to use proposition whatever, I need to realize the sequence AK as a telescoping series. So let's try to do that. And how do people remember the method of partial fractions from calculus 2?
Like partial fraction decomposition?
Yeah.
Oh, crap, I tell you. Yeah, somewhat. It's a move.
So let's use the method of partial fractions. This won't be part of the write-up, because I'm just going to figure out what this is equal to. Let's figure out what that's equal to. So the method of partial fractions says whenever you see a product in the denominator, you can try to write that as something over k plus something over k plus 1. And this is like an aside. This isn't something that would be in your actual write-up. And let's just try to figure out what those somethings are. So if you wanted to figure out what A and B satisfy that, what would you want to do? Yeah.
Multiply the k over here. Multiply k times k plus 1 over on both sides.
Okay, multiply both sides by k. Yeah, that'll do. that'll give me k times k plus 1 equals all over this.
Wouldn't it just be 1?
Yeah, okay, yeah. Not the easiest way to do things, but it'll do. The other way would have been just thinking about how you add fractions.
Yeah.
This is equivalent. So let's distribute, I guess. You got this okay? And we are free to choose A and B however we want. But that equality has to be true for absolutely every choice of K. So one reasonable way to think would be, well, that means on the left and right hand side I see a constant term. On the left and right hand side I see a coefficient in front of K, and that's it. Let's just set the constant terms equal to each other. And this really is like, at this point, impromptu calculus nutshell. I think you can tell, well, no, this would be 0 because it must be. Not that it makes a difference. So what's A?
1.
What's B?
Negative 1.
So this is allegedly equal to by the method of partial fraction decomposition. Feeling pretty good? All right. So by the method of partial fraction decomposition, this is equal to 1 over k minus 1 over k plus 1. I now claim that I'm ready to realize the sequence AK as a telescoping telescoping. There, that's what I think I actually mean. Because it's the series that is a telescoping series. The sequence isn't a telescoping series. So to do that, I guess that means I need to find a choice of CK so that AK is identically equal to CK minus CK plus 1. Based on what we just did, what seems like a reasonable choice of CK? So if we want to appeal to the telescoping series theorem, there's the thing that I need. What seems like a good choice of CK? Yeah, so how about just like that?
Yeah.
So if that were 1 over k, then that would have to be 1 over k plus 1. Okay, is AK equal to that difference?
Yeah.
Groovy. So let's set CK be just 1 over k. Then CK minus CK plus 1 equals 1 over k minus 1 over k plus 1. Hey, is that exactly equal to AK? Yeah, right?
Oh, the order of interest, but okay.
Yeah, some corrections are being made on the fly to polar correctness. Well, CK converges to, what's the limit of the CKs? Yeah, what's the limit of 1 over k as k goes to infinity?
0.
is there a question of the form, I don't know what's written? Is there a question? You just look like there is.
What it was saying like right there.
Oh, if there's extra time, I want to spend it thinking about theorem 5.5.10, which is in the homework. That's a note for me, not a note for you. But that's reasonable that you are upset about that. All right. So have we proven that AK is equal to CK minus CK plus 1? Yeah. Have we shown that CK is a sequence that converges?
Yes.
Is that everything we need to appeal to the proposition called telescoping series?
Oh, yeah.
So what can we conclude?
That A sub k is equal to, what is that, C sub 1 minus C sub n plus 1?
Careful, not n plus 1, because there's an infinity there.
Yeah, which is C.
Yeah, so whatever the limit is.
So I can always further out. Yep.
But what is the limit of this? What is C equal to? And in fact, I guess I could be more specific than that. What is C1 equal to?
Okay, well, Robert then?
Yeah, when k equals 1 though, what is C1 equal to? Yeah, say it louder though.
1.
Just 1. All right, 1 over 1 is 1. In particular, it converges. The fact that it converges to 1 wasn't part of the claim, but it's always nice when you prove something converges by computing the damn limit to write down what the limit is. People feel pretty good? That argument go okay? Cool. So, with 15 minutes remaining, I think what I'd like to do is take a tour of what's in the homework and talk about a particular one of the homework claims. Because that one particular homework claim is going to be very relevant for what happens next, which is the comparison test. So the first is, well, something that's super intuitive. If you have a series that converges and you multiply all the terms of the series by some number, does that multiply the result of the series by that number?
Yeah.
Yeah, good. And you would prove that by using, I guess, limit laws. There shouldn't be any epsilons or big N's in your argument, just use limit laws. And this is better over here too.
Wait, did you say that shouldn't appear?
That should appear.
That should appear.
Yeah, you better have a sequence of partial sums if you're showing that a series converges.
Oh, right. Oh, right. Oh, okay. Yeah.
Proposition 5.5.9, does that look like, let's see, the two other results in here are the geometric series and telescoping series. What setup does this look like you're set up to do? Yeah, I think so. As a bonus, so I'm skipping through intentionally, I'm going to come back to that. You'll prove those two lemmas. Or one of those two lemmas. Either one of those can be proved by induction. Induction isn't the only approach. Let's talk about item 3. So do you remember in Calc 2 there was a special law called absolute convergence? And that's like what you say if a series converges after you put absolute value bars around each of the terms. And it would be really upsetting if a series could absolutely converge, but not honestly converge. Right? That would make that notationally very awkward.
You define absolute convergence here?
Yes. Well, maybe I'll flip to here for where it's actually written down, so I'm not burying the lead too much. A series converges absolutely if the series converges even after you put absolute value bars around each of the terms.
Oh, okay.
And so here's the claim. If a series converges absolutely, then that series converges. The idea is like when the series, if you put absolute value bars around the terms of the series, you eliminate any possibility for like positive terms and negative terms to cancel and kill each other, and so not make the thing explode. If you just forget about that, you increase the chances that the series just gets really, really big. and so diverges to infinity. That's an intuitive argument. But let's actually prove if a series converges with absolute value pairs around it, then that series converges. And there is like this walkthrough on the next page, but instead I think I'm going to take the more relaxed approach of let's actually just write some stuff on the board. So let's try to figure out the proof of this.
Is this something where we're going to write on board, come back to write up, come back to board type thing, or?
I don't know. So since it is homework, I think I'm only going to write on board.
Okay.
So if you want to follow along, and you should grab like some paper if you want to follow along. All right. So I guess maybe the proof should. So here's the thing I get to assume. And all of this is about convergence of series. What does it mean for a series to converge?
That you add, or that the sequence of the series of partial sums.
Yes, you had already thought that sequence of partial sums. But that's fair. It's hard to remember these ones when you're saying it. So let's appeal to some sequences of partial sums. Let's give them a name. Maybe I'll look and see that I'm going to maybe be consistent with. So let's let Sn be the sequence of partial sums for the sum of all of the A plays. So what is Sn equal to?
The sum of k equals 1 to n of a sub k.
Let's let Tn be the other sequence of partial sums relevant to the problem. Alright, so what do I know and what do I need to prove? Are the names of the things the same as in the guide? Okay. There was a 50-50 shot I get it right, even with going back and looking.
So I think we assume that the T sub n converges in this case? Or no, not that T sub n, but that the series it comes from converges, right?
Mm-hmm. Which means that
T sub n must also converge? Is that like a subsequence then?
no, it's a definition thing.
Definition thing. So by definition, partial sums must converge if they converge.
Yep. And that is this definition, definition 5.5.1.
Oh, yeah.
I say that the series converges to L if the sequence of partial sums converges to L. And there's no L there, but that's just because I don't have a name for the limit right now. You could make up a name for the limit if you wanted to, but that's not going to be relevant for what's going to happen next. We need to show, we need to show that this series converges. So what sequence do I need to show converges?
Oh, S sub n?
Yeah, I need to show the sequence of partial sums for this series converges.
Oh, okay.
So I need to show that Sn converges. I have no to show that a sequence converges without needing a guess for what the limit is. Yeah.
Is that the Cauchy criterion?
Yeah, the Cauchy criterion is one of the options. I guess there are like 3, but I can think of right now. The Cauchy criterion, monotone convergence, and the theorem of contractive sequences that you proved in Google.
Oh.
But, I mean, let's process of elimination is, if the AKs aren't all positive, is this monotone?
No.
No. So monotone convergence is out. I don't know that it's monotone. Contractive is like too strong. I don't think that this is probably going to tonic be contracted. So let's try to show that the thing is Cauchy. We will show Sn is Cauchy. Right, because if we get that it's Cauchy, every Cauchy sequence converges. So Sn converges. So the series that Sn is the sequence of partial sums of converges. All right, so if I'm going to use Cauchiness, let's also translate Tn to Cauchiness. Because Tn converges, what can you tell me about Tn?
There exists some big N so that...
What you're saying isn't wrong, but it's not what I would want. I have no idea what the limits are.
Okay.
So what you told me already is, if I can show that Sn is Cauchy, then Sn will converge. I know that Tn is convergent, so what can I conclude? Tn is Cauchy, right? Cauchy if and only if convergent. As Tn is convergent, Tn is Cauchy. And now, let's go and actually show that this sucker is Cauchy. So, well, what's like the formal statement you need to prove to show that something is Cauchy?
There exists some M at big N, so that for all little m and little n bigger than big N, the absolute value of their difference is less than epsilon. I think there might be a for all epsilon greater than 0 in there.
Yep. So there's the thing that I need to show. So I better start by considering any epsilon bigger than 0. Now I need to come up with a choice of big N. I don't know what any of the sequences are in any sort of real explicit way, so I'm not going to come up with an explicit choice of big N. There's no hope of that. But I know that Tn is Cauchy. So since Tn is Cauchy, what can you tell me? Well, like that, right? But with T's instead. Since Tn is Cauchy, there exists a big N such that for all m and n bigger than big N, all right, so
I'm trying to follow along in sort of the write-up outline, and I'm a little lost at maybe, because we had to consider any epsilon greater than 0 since I said T sub n, correct, is Cauchy, then there exists some big N so that the thing holds.
yeah.
But then, wouldn't that be T sub n minus T sub m is less than epsilon, not the line that we wrote? Okay.
I do have T sub n minus T sub n less than epsilon.
Yeah.
So this was like you reminding me what the definition of Cauchy is.
Oh, that's just a side thing.
Yeah,
Okay.
this was the side.
Okay, all right.
So this is the, if you like, there's the want to show.
Okay.
All right, so now like we just have to mess around with that difference. All right, Sn minus Sm. What is Sn?
So we have the absolute value of k equals 1 to n
ones have a bunch of columns in common, don't they?
Yes.
Either the plus m columns are all in common if m is the small law, or the plus n columns are all in common if n is the small law.
This is sort of a side note. I don't want to like pull us off the part, but like since we have m and n, how can we assume it's all sort of predicated on the fact that we know that m is greater than n? How can we assume that without loss of generality?
Look at the statement. So if you knew that statement, whenever n is bigger than m is bigger than big N, everything in that statement is totally symmetric in m and n.
Okay.
So if you knew it with m and n in one order, you would know it with m and n in the opposite order. You just switch the order.
Okay.
Alternately, if m and n were in the wrong order, you would just like switch the order of sums.
Okay. Oh, right.
Cool. And I guess I'm running low on time to actually finish the argument, but maybe combined with looking at what's actually on the table. Do you believe that you are capable of finishing this argument?
Possibly.
Yeah, so a bunch of the things will cancel. You'll be left with a sub-sum. Now it's a single sum, and you'd like to get this thing involved. So right now you have the sum over whatever bounds. If you move the absolute value varies to the inside, does the sum get bigger? Yeah, that's like the triangle inequality.
Oh, yeah.
The n-term triangle inequality, many-term triangle inequality. I'll be out in a second. But then eventually you want like things that look like this to show up. But right now you see only like a single subsum. Oh, but you can do the same thing as you did to get to the subsum of backwards. You like anti-cancel a bunch of things. Well, what does that mean? That means add and subtract some things that would cancel. Oh, hey, and then once you do that, then you have Tn back.
Okay.
Cool. Yeah.
And the very last line, is that supposed to just be epsilon sitting there?
Yeah.
Okay.
So that's the dream. You need to get that to be less than epsilon.
Great.
So if it takes you more lines than that, that's fine.
Okay.
You're not obliged to use exactly this outline.
I don't know what you're talking about. Oh, I'm just messing with it.
Oh, okay. Yeah. Well, you can still look at it though. You should still know that it's there.
Yeah, okay.
But if you want to expand things in more steps or use different steps, you have freedom.
Oh, all right. Cool.
People feel pretty okay about how today went?
Yeah, actually, I kind of liked it. I feel like it's getting easier in the course the more tools we have. Because at the beginning, I was not understanding hardly anything